Okay, welcome. The purpose of this video is to give you an introduction to a library system for SQLite. It's an architecture for Unity 3D using LINQ and enterprise design patterns. And what I'm going to do is go through this deck and give you an introduction to what SQLINQ is and how to use it. So you can get more information about this utility library by going to games.elenesski.info, and that will give you additional help and support, tell you about all of my other games, my music, and some other stuff. In the videos, this video is all about understanding the architecture of SQLINQ. There is a second video that describes how to do modeling with the sim tool, which I'll describe later on, and how models get transformed from sim into code, and then other videos we'll get to find later on. It's important to remember that inside the YouTube description text below, you'll see links to various parts of the video. So if you want to jump ahead, use the description in the video text to jump forward to another section. The overview of this presentation is I'm going to give an overview of what SQLINQ is. So it basically provides an interface and architecture for SQLite where you almost never have to actually write any DDL or SQL. So DDL is the data definition language. That's like create table, create index, that kind of thing. And SQL being your selects, inserts, updates, and delete statements. So with this platform, you'll never have to write any of that stuff. You can, obviously, but for the majority of things that you do, you don't need to write any of that SQL code. I'll talk about the architecture, I'll talk about the generator, what the sim tool is, and then I have some sort of snapshot code examples that I'll show you. The other video will have a walkthrough of the actual modeling process for the tool. And then it will show you almost like a deep dive into some of the code that gets generated for it. Why are you freezing? Okay. The computer froze there for a moment. Anyway, requirements for SQLite. Basically, you need a 32 or 64-bit version of Unity 3D. A compiler flags switches between 32 and 64-bit SQLite DDL, which is included, or DLL, which is included in the Unity package. It requires a Pro version or a version 5. The version 5 free version, and the reason why it's version 5 personal is because in version 5 they basically opened up all of the features for the free or personal version, which includes the requirement to link in a DLL. This doesn't work in Unity for free, so that's the trade-off. So what is SQLINQ? Well, it's basically two Unity 3D class libraries and a generator that provides a mechanism to implement a layered and pattern-based architecture on top of an object relational map. So an object relational map is basically a platform to allow you to represent your objects in code and then turn around and say, I want to save that object away in the database. And so the ORM basically says, okay, here's your object, I'll persist it in the database. Or if you're sitting inside your domain and you want to get some objects out of the database, you go to the ORM and say, give me some objects out of the database. This platform is a little bit more sophisticated than that sort of simple overview, and that'll be pretty clear as we get through it. So SQLINQ is implementing the following two sort of major features. It implements the link table interaction. So basically you can use link statements to interact with SQLite. So you don't actually have to write any SQL code. And that actually comes from a free library that's embedded into SQLINQ. What you're really paying for are all of the design patterns and the generator, which is, I think, pretty sophisticated. So we're implementing Martin Fowler enterprise architecture patterns. So if you do a search for Martin Fowler, if you do a search for them online, you'll find a library of all of the design and enterprise architecture patterns that he has published. And also we'll be using some Gang of Four design patterns. So design patterns are the original design patterns that came out in the 90s. It sort of kicked off the entire pattern thing. And Gang of Four, refers to the four authors of that original text. So the SQLINQ Generator, basically what it does is it transforms a UML class model. It's actually, it's not a true class model, it's only the attributes of the class model, into three C# source code libraries to form this layered architecture. The C# code libraries are then generated directly into your Unity 3D project, and you can compile them immediately, or you can look at them first, obviously. And it's designed for iterative development, and it uses internal logic and external code templates so that you could potentially change how it all works and generates. It's actually not that hard. Yeah, I think that's all I have to say there. So the implemented patterns, so again, these are Fowler and Gang of Four patterns. So these are all the patterns, and I'm going to go through in fairly, not incredible detail. Identity map, there's a lot of detail, but the rest are fairly fluffy. So the first pattern is Fowler's identity field pattern. And what this allows you to do is, or what it does for you, is it automatically generates an object identifier. Object identifiers are 32-bit integers. I did consider using GUIDs, and I felt that was overkill. So that was sort of the decision I made. Every persisted OID is the value 1 or larger in each table. So when you create a brand new instance, the OID is set to 0, so that tells me that this has not been saved, and any OID that's 1 or larger means it's in the table someplace. OIDs are also handled automatically for lazy loaded master-child associations, which I'll talk about in a second. And these get transformed into foreign key relationships in the tables. So what I'd mean by automatic OID handling is, in this example here, you have a room definition and a table or a door trigger, and so you don't need to define an OID inside of this class definition. You just basically define the attributes that you want. That's sort of one thing I was trying to remember to mention earlier, is that it's a partial library. You're only defining the attributes. There's a way of defining the behavior inside your code, and I'll talk about that later. Anyway, so the classes in here, you just simply identify the attributes, and the generator will automatically put in the OIDs for you. In the association that you have here, basically what happens is the system will automatically generate additional attributes. So in the room definition object inside the class, it'll create a new attribute called triggers, and it will contain a reference to all the door triggers that are associated with that room definition. It implements an iList, which gives you a whole bunch of list features, and of course iList implements iCollection and iEnumeration. So you can actually enumerate through the list fairly easily, and you can also use link on the associations. You can say stuff like my room definition dot triggers dot where, and then give some predicate for the where clause. And I just have one little note here is, if you're looking at this, you may want to investigate the lazy load children after add event. So basically what happens is, when you're actually inserting new door trigger instances into the triggers list, you can be notified of when that happens, because sometimes it happens automatically, or it kind of happens kind of in the background. So sometimes you want to be notified of when that happens sort of independently. Also automatic OID handling for essentially what I call foreign keys. So the door trigger will get an extra attribute called the room, and it contains a reference to the room definition associated with the door trigger. And then in the underlying table, it creates a foreign key relationship called the room OID. So that's what the identity field does. the identity map is it's a really subtle feature that gets added, and it has really powerful implications. If you don't implement an identity map, you have the chance of corrupting your data. So let me go through an example of what I mean by how you can corrupt your data. And this particular bug is really hard to find, this corrupted data bug. So hopefully you'll appreciate what the identity map is doing for you. So let's go through a really basic example of how to deal with objects in an ORM. So here we have we're working with an object. We're calling the object Albertville, has population of 17,500 and a growth rate of 1.7. And that's what's stored away in the SQLINQ database. When you're dealing with an ORM, you are typically dealing with full copies of objects, all the attributes, and you don't really think about the individual data elements or table columns. The reason you want to take this strategy is because you want to be able to rename things, move things around. You want to really think about objects in terms of the functionality or the behavior that the objects implement, not the attributes that those objects are implementing. So it's really important to think about it that way. And by not creating references to your data elements inside your code, you in fact are decoupling your table definitions from your domains. So it's kind of an important thing when you're dealing with objects. So we want to do what seems to be a really simple process. We want to update the population. We want to update the growth rate. Now I've labeled these as two separate boxes to imply that there's two separate pieces of behavior going on with the town. Now if it was one piece of behavior, it should be one box saying update the population and the growth rate, but here it's two separate boxes, which means they should be able to occur independently of each other without contaminating what the behavior is doing. So if you don't implement the identity map, which I'll talk about later, you have the potential of corrupting your data. And let me show you how this corruption takes place typically. So what you do is, first of all, you pull out of the database a copy of the object, and then you set the population to 19,000. At some other point in your code, you update the growth rate to 2.2. So to do that, you pull out of the database a copy of this particular town, and you set the growth rate to 2.2. So you have basically two instances, one with population 19,000 and a second one with growth 2.2. You come along and you say, I'm going to update this instance into the database, and I'm going to update this population into the database, and then you come along later and you update the growth rate into the database. So what do you think is going to be in the Albertville in the database for Albertville? And the answer is the growth is 2.2. And immediately you should be wondering, well, what happened to the population update of 19,000? So this is the corruption that I'm talking about. So we know clearly that we updated the population. We wrote it out to the database. But then what happened was we updated the growth rate. And because it was a separate instance, and because we said update, we wrote out all the attributes. So Albertville, population of 17,500 and growth 2.2 was written out to the database. And you're thinking, well, why didn't the second instance have a population of 19,000? And that occurs because when we pulled the instance, the 19,000 update of the population was not in the database. So this is the kind of corruption I'm talking about. So when you're dealing with objects, you're really trying to deal with objects as a full thing, all the attributes. So that's why when the second update took place, it overwrote the population. So to fix this problem, you use an identity map. So again, we're going to go through the same process. We're going to update the population. We're going to update the growth rate. We pull out of the database an instance that is Albertville with all those attributes. And then we pull a second time out of the database to pull out Albertville and the population. And what the identity map does is it guarantees that we're dealing with a single instance. So the way it works is when you pull from the database the first time, so this pull will tell the repository object, hey, do you know about this instance? If the answer is yes, it'll return that instance. If it's no, it'll store that instance away in a map and then return the instance, the appropriate instance for it. When you do this one, it asks the same question again. Do you know about this instance? And in this case, it's yes. So it's going to go into the repository, is going to pull the instance that had been previously pulled and returns that instead. So you get this single instance. So when you actually perform the update of the population, you're essentially updating it in both locations. So, I mean, because it's the same instance, this update updates this, and of course it updates this. And then when you update the growth rate, same thing again, you're updating in both locations. So it doesn't really matter now whether you update from 19,000 this behavior first, or you update from this behavior first. You're going to update the same instance, and of course then the object is properly reflected in the database. So that's what the map does, and it's the way the architecture works for SQLINQ. This entire map process is completely transparent. So it happens in the background, it's all automatic, works great. Yeah, that's basically what it does. So the next pattern is a single table inheritance pattern. So basically what this does is it allows you to use a single database table to represent several related classes. So here's a object. This is actually from one of my games, or one of the games that I'm writing. It basically shows that a star object, a nebula object, and an anomaly object are subclasses of a base class called space object. And what single table inheritance does is it uses a single physical table, so one table, to basically store the base class and all the subtypes. So basically, if you were to look in the definition for the table, you'd see all these attributes, all these attributes, all these attributes, and all these attributes stored in a single table. And then what happens is when the table is being loaded out of the database, there's an automatic subtype field that also gets generated, and it's used with a factory method to basically construct the right objects. So the subtype will be star. So when it's a star, I know how to construct an object passing in all these attributes and all these attributes. And when it's a nebula, all these attributes and all these attributes, and so on and so forth. So it's an automatic transformation of the instance in the table to a domain object that contains a bunch of attributes. There is one rule that you need to know about, and that is that you can't use the same named attribute within any subtype. So for example, if these two pieces here wanted to use name, you couldn't do that. Now you can sometimes resolve that problem by introducing a abstract subtype in the middle of your inheritance hierarchy. Generally just rename it. It's really not that big a deal. Other SQLINQ patterns is the unit of work. Normally you don't use the unit of work. It's an additional feature that's been added into the framework. It was there from the original version of the framework before I converted it for Unity 3D. So essentially you're using a library that's pretty stable, but of course it's been converted to Unity. Again, you don't need to use a unit of work normally, but the functionality exists so that you do have the option. And what a unit of work is, it allows you to save several objects into the database as a set. So basically, if the set doesn't work, if one of the objects doesn't get inserted properly, it'll basically cause the entire set of objects to not be stored in the database. So it allows you to work in terms of sets of objects rather than individual objects. For a lot of users, writing individual objects out to the database one at a time is good enough. And there's basically validation logic that happens in the background as well. So it might be that there might be a rule that says the growth rate can't be less than 1. So this particular object here is going to fail because the growth rate is set to 0.7. And the other thing it does is it uses the dirty flag. So basically when you set one of these values, it sets this dirty flag saying, hey, this instance has actually been modified. And there's a single call that you can make, and what it does, it takes advantage of the memory map that's used for the identity map to decide which objects are dirty and write those out. So even if in memory you might have 100 objects and 3 of them are dirty, I basically just loop through all 100 objects and say, are you dirty? Yes. Are you dirty? Yes. Are you dirty? Yes. And if the object is dirty, then I write that object out to the database. So it's basically a single call to actually do the unit of work. And the way it works is it starts a transaction, tries to write them all out, and then if it can't, it basically fails and rolls back the transaction. And it also restores the state of the objects. You can look in the repository for more information on how that works. Lazy loading is a really powerful feature. Basically, suppose you have this reference. So in the past, or earlier I mentioned that, for example, you have a room definition. It'll create this attribute called triggers that contains all these references. So let's suppose you have a room definition called my room, and you want to get all the room's triggers that aren't in memory yet. So how do you do it? And the answer is really, really simple and straightforward. You just simply reference room.triggers. So you could do this in a for each loop. So you could say for each trigger in my triggers and just loop through them. And it works as if the objects were already in memory. So simply the referencing of triggers will say, has this been loaded? No. Go out to the database and grab all the instances and pull them back in. Works the same way for the master. Basically works the same way. So how do you get the room's name? Well, you just simply reference it. Say my room, or my trigger the room name. And when you reference the room, it basically loads in that reference into that object, and it looks as if the room was always in memory. Gang of 4 factory pattern. Basically, it's used to resolve subtypes used by the single table inheritance pattern. And basically what it does is it uses the subtype to figure out which domain constructor to use for a row instance. And finally, the gang of 4 bridge pattern is used in the generator. And basically what happens is I use a tool called sim in order to represent the UML class model. And when you take that class model and transform that into code, I create an intermediary object that sits, or an object specification that sits between the two, that basically transforms the model into this intermediary format, and then I generate this from this intermediary format. So what that allows you to do is, if you don't like using that sim tool and you want to use your own tool, or you have some other mechanism to represent all your objects, you can create your own bridge for the way you represent your objects and generate from that specification. The bridge implementation for sim took me about 2-ish days to implement, so it really wasn't all that hard. And so it's actually a very powerful capability. It also introduces some abilities to have asset store stuff, and I'll talk about that later. So the SQLINQ architecture. So this is really talking about how do you get the data to and from SQLite from your Unity 3D classes and scripts. So it all starts out with your code calling a SQLINQ domain class. So this is a class in your domain. This piece gets generated, and I'll talk about that in a little bit here. But basically you make a request to the domain to do something, and that request could be give me some data, save some data away, delete the instance out of the database, a bunch of stuff like that. And so this domain object will then in turn interpret your domain-like request, transform that into a table request, The table request calls a library called SQL.net. This is actually a library that is embedded into the tool. I didn't write it. That's described in the specification. This library then calls SQLite. SQLite returns back into the SQL.net environment and then passes the data back into the table. Now, depending on what you were doing with your domain, the table may, if it's like an insert, update, or delete, the table will call the domain or return directly to the domain without any extra functionality, I guess. And that will then go back to your code. If you're doing a select statement, the select statement goes into a factory. So the factory is essentially the factory method, and what it's trying to do is deciding which constructor it will use in order to create the domain object. But it does one extra step, and that is that it uses a call to the repository to determine whether or not that object that I'm pulling back from the database is actually in memory already. If it's in memory already, I essentially drop the instance that came from the table and replace it with the in-memory object version and return that instead. Or if it's new, then the repository will basically construct a new instance of that object and store it in the repository, so that if it's requested again, you get that instance instead of a new one. Again, once it comes out of the factory, it goes back into your domain and into your code. So the objects here in green are basically pre-written pieces of code that are embedded into your application, and the blue objects are generated. Generation is done iteratively, so throughout your application development process, throughout the development of your game or your Unity application, you can regenerate these classes hundreds of times. And so to make the generation work properly, I generate partial classes. So it goes in, and the generator will create this generated class, which can be regenerated multiple times. But the big question comes up, well, what about the behavior of your class? So the classes that get created are just the attributes, the things that get stored away in the database. But what about your behavior? Like when you're validating logic, or you want to do some calculations against some of the fields, where do you put that behavior? And the answer is it's a partial class. So because the because the table, domain, and factory objects are partial, you can create your own custom extensions that contains your behavior for that same class, and you mark them as a partial. And this is a C#. I think it came out in Framework 3. But basically, when the compiler happens, these two classes are linked together so that your code sees them as a single class. So it's a really powerful feature. This way you can actually replace these generated classes all the time without affecting your behavior. So this is how it regenerates multiple times, and the specification for the generator actually comes from something called which I call the SIM model, which I'll talk about now. So the SIM model is the Software Ideas Modeler. It's a Windows only UML tool. If you don't want to use this tool, or you're on OS X, there's a couple of other options you can use to have access to this tool. And I'll explain why I picked this tool over other potential tools. So what is SIM? It's basically a diagramming tool that allows you to specify your software details in UML, and it runs in Windows. Why did I pick it? Well, first, it's actively being developed. So this video was recorded in March of 2015, and the last version of SIM was released in February. So it's an active tool. It's a really great tool, has a bunch of features, and for me, it comes with an XML file format. So basically, you're working in your model. You save your model away as a standard SIM model that gets stored as an XML document, and I can parse that file directly and generate code from it. So it's really useful for that. From a licensing perspective, if you're in a commercial environment, so you have a game or an application that's actually generating money or intend on generating money, then the cost for the tool is really inexpensive. It's only like $45 per person, and there's discounts for volumes and stuff like that. But more importantly, if you're using the free, if you haven't monetized your game yet, or you're still trying to figure out how to make the thing work or make money from it, if you're in a non-commercial environment, the licensing is free. So that's a really beneficial thing. If you do actually use the free version and you start making money, you're obligated to pay the licensing fee because, of course, now you're in a commercial environment. So do the professional thing and pay the licensing fees because, of course, the person who wrote the tool needs to make a living as well. Now we looked at tools for Mac and Windows, and there was basically two requirements. One is they had to be free for non-commercial users. That was a really big piece, right? Because on top of the SQLINQ library for Unity, I don't want to have people spend a whole bunch of extra money for a tool. So there were tools out there actually that had easy ways to transform the models, but then they also had like a $80 licensing fee for the tool itself. And it was sort of like, well, do I really want to force people to spend extra money for a tool? So that's actually the reason why I picked Sim. So if you're an OS X developer, you basically have two options. You can use the Windows Bridge. So I'm assuming that if you're an OS X developer, you have Windows access. If you don't, you can write your own UML parser, which I'll talk about next. So can you use other tools? Well, obviously you can, because I told you about that in the last slide. The generator uses the gang of four bridge pattern to transform the sim model into an intermediary object model. There's one line of code in the entire system where that actually takes place. It's early on in the generate code method inside of the SQLINQ generator. And basically it's a static class. It takes a UML model parser and parses a file. So you could actually replace the UML model parser with your own class and parse any UML model to your heart's content. So if you're already using in a UML modeling environment or have access to one and you don't want to pay extra fees, well, you can write your own bridge. Like I say before, the bridge that I wrote for the Sim tool only took me a couple of days. So it shouldn't take you that long to re-implement the model yourself. So any tool that can create this intermediary object model will work. All you have to do is represent classes, connectors, generalizations, connectors being associations, generalizations, attributes, stereotypes, and subtypes. I use tagged values in Sim to represent subtypes. Other tools may not have that flexibility, so you have to figure out some way to represent all these things. Now, one thing that's kind of important and kind of funny at the same time is you don't actually need to use a UML modeling tool at all. If you really want to and you really need to, you can actually use spreadsheets. So if you think about it, all you have to do is figure out some way to represent these 5 things, 6 things that I've mentioned. You can do it in spreadsheets, text documents, XML documents, doesn't really matter what it is. If you can write a converter that takes your spreadsheets and transforms it into a generator spec object, perfect, works great. So that's kind of cool that way. The bridge also allows other developers to create add-on functionality, and if you want, you can even put it in the asset store. So basically, you just write the code to have your own UML model parser. Not saying you have to, but you could. In order to save, delete, and validate objects. So this is sort of the next major part. So now we've kind of described how all the architecture works. So how do you actually make some of this stuff work? So deleting is done in 2 stages. You basically tell the system, I want to delete this instance, and to make it permanent, you say save. The validate is automatic in the save method. So whether you're doing an update, insert, or delete, you can figure out which kind of validation you need to do. The definition for those 3 properties is in the base class. So if you want to look at the base class, that's where they're defined. And then if you want to get validation to fail, you just simply add an error message type to your validation, and it will prevent the save from being written to the database. So saving and validation, I'll talk about delete next. So this is how you do a save. It basically consists of validation, saving, and returning results. So in validation, you basically say you're going to do a save and you're going to return a validation result. So basically you create validation messages. You can override the validate, which I'll talk about in a bit. And if there's errors, it exits automatically. If it succeeds with no errors, it goes directly into save. So it writes all the attributes out to the table, and then it saves it in using the repository. It saves it out. And the repository has some generic code that basically handles the save. Once the save is complete, I test to see if it was successful. So if repository.save failed to write the instance out, it will return false. So if the result is false, I'll add an error saying it couldn't be written out successfully, give you some contextual information, and then return. To overwrite a validate object, you basically go in there and you say, add some validation logic. And here I'm just throwing in some examples. So you basically need to specify the type of message and the message you want, and then you can have an optional context. The only requirement that you really have with validates is if your code will issue multiple validation messages, your Unity program will have to know how to interpret that. So typically most environments you'll have a single message, and you only have to handle a single message. Or if you're going to do multiple messages. So that's maybe one potential issue, is that if you have multiple messages, your Unity environment will have to handle multiple messages, which may or may not be easy depending on what you're doing. If you have no errors, you basically just return the new result instance, and that's the default functionality that's in the base class. So deleting objects. A deletion in SQLINQ is nothing more than a flag when you call the method delete. So in order to make it permanent, you say delete and then you do a save. And this approach is required for a unit of work. So that's the Fowler's unit of work that I talked about earlier. If I were to write the code to say when you called delete, it automatically deleted it out of the database, did an automatic save, what would happen is you would violate the principles of having a unit of work. So that's the reason why it's there. And then unit of work saving. This is a really simple slide. You basically call the repository, and the validation result will delete it and save it, save it as a group, and if it fails, it will return the validation result. It's actually just a really simple command. And the way this works is it uses the identity map to basically scan through the entire environment, and uses the identity map and tests to see a dirty flag. And if you have 100 objects in memory and 3 of them have been modified, then their dirty flags will be set to true. I just loop through all 100 objects and I say, have you changed? Yes, I'll write you out. Have you changed? Yes, I'll write you out. And that's the way it works. Pretty simple. Additional calls to the factory and the repository. So I've implied that through this model you only call the SQL domain. Well, that's not entirely true. What you will do actually is call the domain, the factory, and the repository with some extra functionality, and that's what this section's about. So in the generated factory, you will call the initialize. You need to initialize the environment with the factory.initialize at least once in your code. It's a kind of a smart implementation, so that if you call it more than once, it will work the first time, but the second time will just exit, saying, well, it won't say anything, it'll just ignore it. And then if you're creating a brand new database for the first time, you basically tell the repository to define where the SQLite file is stored on the hard drive, and then you call make database, and then that will construct all the tables and indexes if you have them defined, stores those away. So here's in the repository, here's how you initialize the repository. You just give it the name of the file. SQLite doesn't care about the extension, so you could call your file name .db or don't have an extension, or .text or whatever you want it to be. It's just a place for it to store information. If you're creating a new database, as I mentioned before, you initialize the repository, and then you call factory make database, which will construct all the tables. And if you want to do a unit of work, which again I've mentioned before, you're not obligated to use units of work, but basically you go to the repository and you do it at a .commit. So how do I start the SQLINQ generator? It's actually really straightforward. The setting of this is covered in the modeling overview video, but in our environment, it's basically a script on a game object. You specify all these attributes, where the name of the sim file is, the name of your namespaces, where the templates are stored, and where your code is generated, and then click generate code. If you want to debug the generator and see how it works, what you can do is you can turn on debugging, put a break line someplace in the code, and click the script debugging, turn that on, and then you don't click generate code. What you do is you start the game. You start your application inside of Unity, and then during the start of that script is when you'll actually do the generation. Yeah. So I'm going to go through some basic features by example, and then some more detailed ones later on. So here's the generator example. So given all the functionality, you can imagine how much code might get generated. So there's a single class here with 2 attributes, and when I generate it, it generates all this code. And of course you're wondering, well, why is there lots of lines of code? Well, you've seen a whole bunch of functionality, but there's additional things that get generated. First off, this is sort of the introductory part of the table, and I'm breaking down the code into chunks so it's easier to understand all the code. The first thing you'll notice is there's comments. So at every opportunity where I can generate a comment, there's a comment inside the code. So you can all the documentation for your class can be specified inside the class, and then it gets generated in throughout the rest of the code. The code also has to be maintainable, so if for some reason the tool can't be used or you go in a different direction, the resulting code has to be usable as if somebody actually wrote it for real, rather than just A, B, C attributes and stuff like that. So I tried to make the code as if I had written it myself, and so that I could actually maintain the code without the tool. Hopefully the tool, you never have to make that decision, but that's the reason why there's blank lines everywhere, comments everywhere, extra features everywhere, and so on. All objects are generated with a partial, so when the things are being generated, it's generating just sort of the attribute side of things. And if you want to put in your behavior, you basically construct another file. That file will be anywhere in the hard drive that you want. That's obviously has to be in the assets folder inside of Unity. You give it the same namespace and the same name here, and you specify that it's a partial class. And when it's compiled, the compiler will link the 2 pieces together. So behavior is in one area and the data is in another, and that's how you construct the behavior. Automatic creation of the OIDs and the subtype. Subtypes used by single table inheritance to resolve which constructor to use when rows are pulled out of the database. Here's an example, again, of the attributes that were in the original table. There's a table method that gets created that allows you to construct the table. And one important thing is I do get a temporary database connection, so that if you're in an iOS or a mobile environment and your application fails, if you have a database that's left open and your application fails, you have the potential of corrupting the database. So by having a temporary database connection, you minimize the impact of something like that. The system also generates 2 find methods, one to find individual OIDs given an OID identifier, and a getAll method that allows you to get all the attributes or all the rows in that table. And there's some variations to getAll, which I'll talk about later. The domain class looks like this. Here's the definition for the subtype. Attributes are defined like this. So basically you have a protected internal variable and a public property. So the getter just gets the internal variable, and the setter basically tests to see whether or not the value changed, and only when it's changed does it set the value and set the dirty flag. So this is how it figures out whether or not an object has been modified or basically been set. Dirty flag. This is the constructor. So there's actually 3 constructors in here. I'm not showing you one of them. But basically when you create a brand new instance, you specify an OID. The other thing you can do is you specify all the attributes. So it's a public constructor, and you basically put 0 in for a new object and then specify all the appropriate values. And there's some extra steps you have to do when you're constructing an object and then needing to associate that object with something else. But that's covered in the model overview, not in this video. A domain example. So when you actually pull objects, so these are the 2 default objects that get generated. So get by OID and get all. So here's the state, trigger state table. So the table get OID. So basically this thing comes back and then it gets routed into a factory that's on the repository. So this is actually the way it's configured. Is it goes into this, there's a factory method that initializes all these factory components. So you can pull this into the factory, it transforms these tables into states and returns that. So that's how it's able to figure this out. And then you can also transform multiple instances so it becomes an enumeration. The utility class, this is the thing that initializes the repository's factory. So there's 2 steps in the initialization. The first one is to identify the method that uses or that finds individual object instances when you have just an OID. And then there's another one that defines what I call the read factory. So how you transform tables into object instances. You make reference to a method here. There's a make database. Normally you don't call this directly. It's actually done inside of the actually I lied. You do call this directly. So the state table gets this create table thing created for it, but you call the make database, and so if there's multiple tables in the system, these are all listed one after the other. So it's like create table, create table, create table. Example, this is in the read method. So this is where it's transforming instances out of the table into domain objects. It figures out based on the subtype which constructor to create and then calls that constructor. So if you had multiple subtypes, you'd see this listed multiple times. So I'll go through some other examples in single table inheritance. This is kind of what it's generating for you. So there's a trigger state, and door trigger is a subtype of trigger state. So you'll get a single trigger state table that gets constructed and 2 objects. So these 2 objects get stored in this table, and when you're loading objects out of this table, they get transformed either into a door trigger or into a trigger state based on the subtypes. So here we see the generation of the subtypes. So obviously all the trigger state object attributes get pulled here, and then you'll see the corresponding objects, attributes from door trigger get generated below here. And again, here's the example of the read factory. It basically interprets the subtype and decides which constructor to create. And the constructors look almost identical, but in the door trigger one, there's this scene name which refers to this. There's this scene name which refers to this scene name here in your UML model. And the subtypes come from the table. So in SIM, I use a tag value to represent the subtypes. Again, all that is described in the modeling video. Find methods. So this is a extension that allows you to find methods or find attributes based on variables. So you basically create a stereotype called find on the attribute, and it generates some extra capability in the table and in the objects. So in the table method, this is what it looks like, and I'll just jump ahead to the next slide here. So it does an intelligent kind of test. It doesn't do a select star from table and then use an in-memory loop to test to see the scene and the subtype. It actually does this proper code generation here, where it tests the scene name and sets the tests the door trigger. And what's really important to know is that if there was some subtypes happening up here or some tree happening, then this method gets generated a little bit differently to handle all the subtypes. Yeah. And then here's the domain method. So the domain method basically comes along and says, find the this is not right. It's actually going to be the trigger state table that gets returned. Anyway, there's a bug in the slide here. This will actually return this is sorry, this slide's wrong. It'll actually enumerate through door triggers, but it will actually transform a trigger state table into a door trigger. Sorry about that, but that's how it works. Additional attribute stereotypes. You can put in an index. So here's the find, but also with an index. So if you put in the index here, you should be careful not to put in too many indexes into your code. If the number of instances in your database is less than 100 or so, typically an index is actually less efficient. And it has to do with the way in which most databases work. Instead of individual rows being stored, they're actually stored in clusters of rows. And to do a full table scan, it reads out clusters out of the database in order to do a search. So it's actually faster to load clusters, which often contain 20 to 30 rows, and do an in-memory search than it is to actually use the index, because now you have to load in the index, you have to scan through the index, and then you have to then load a cluster anyway to pull out the row of interest, and those extra database IOs actually take more time. So that's just something to keep yourself aware of. Don't use indexes on tables with less than 100 instances. You can also do a not null. So basically you specify not null in the attribute and it will generate a not null in the table here. This doesn't work for subtypes. In fact, you get an error if you try to do it, because if you were to add it to a subtype, then all variations that weren't direct descendants of that particular class could never be saved, because in the database we're still storing an attribute column called name, and it would be null in all cases that weren't that type or direct descendants of it. So it's restricted from happening. Enumerations. So this is working with restricted values. So in the door trigger class, I've added a type called door type, and it's an integer. And what we really want to do is use an enumeration to work with the door type. So we can do that by creating an enumeration called door types. So here's all the door types with their various values. And what happens is inside the domain, the door trigger door type is defined as a type of door types. So even though inside of the definition here it's an integer, inside the domain it's actually defined as a type of door types. And when the door type is automatically cast to door types when it's constructed. So we put a cast to get this door type out, and it's cast to an integer when it's saved. So that's actually how it handles this the enumeration. So the code that gets generated, so here's the door types that gets generated with all the appropriate comments. And then when the domain takes place, you basically have, so this is how the domain is actually defined inside the door types. It basically transforms this into door types. And so you see it only as a door type. When it's constructed, it's actually cast into door types. And this is public now. Also, in the save method, the door type is cast from the door type. So this door type is an integer. Numerations are integers by default, and this gets cast into the appropriate integer before it's saved away in the repository. So in summary, SQLINQ is a static and generated architecture that's based on a class attribute model. It's C# generated code that implements several patterns to remove the need for you to code any SQL or DDL statements. Uses a default modeling tool called Sim that's Windows based, but other models can be bridged into the generator. And partial class generation means you can maintain your behavior as your schema is regenerated. So all, I think, really powerful features. It implements all these wonderful patterns. Again, if you want to look online under Martin Fowler's Enterprise Architecture Patterns, you can find information about all these patterns, and Gang of Four is written up in Wikipedia. So it generates a multi-layered architecture. So basically there's tables and domains and an underlying factory library as well for something that looks like this. The domain features have all these wonderful features, partial classes, dirty value assignments, and, well, you can read the rest. It has all these wonderful table features, single table inheritance, OID generation, automatic handling of gets, and all that kind of stuff. Has some nice factory features, and yeah, thanks for watching. So if you need more information about SQLINQ, check out the website at games.elenesski.info. Thank you for watching.